Thank you for the invitation. I think this is the first time I'm using the system, so I'll try to do my best. If there's anything, you can just make a gesture if the sound goes up or something. Just again to confirm, everybody hears me? Yes?
Yes.
Good, thank you. Okay, so I'll give a talk, general idea about the kind of research I do on the theory of large deviations. And I'll try to give some historical context to this and some ideas about applications in physics, but also in mathematics. So I'll start with the... large deviation theory is actually a field or an area of probability theory that's dealing with typical states or stochastic processes in general of many kinds, and then I'll be mentioning many kinds of stochastic processes. But it's a theory of fluctuations. So it's a theory to calculate probabilities and probabilities of rare events or fluctuations. And at the same time, it's a theory that can also study typical states, and I'll try to make this precise as I get along in the talk. And it's a theory that's been applied mostly in systems that have many components. So it could be many particles, it could be many Qs interacting together, or many types of system that has many components. So we'll get to see this also. I'll get to define this. What's interesting about the theory, and I'm showing this here on the slides. I don't know if you can see the cursor. Yes. So this is the mathematical. This is actually the physical stream of the theory. This is the mathematical stream of the theory. So if you ask physicists when this theory started, they will probably say that it started with a calculation of Boltzmann, and I'll present that calculation in the next slide. But actually, I'll try to make a presentation, historical presentation of the subject. And this is very interesting, actually. We'll see this. But if you ask a mathematician, they'll say that large deviations theory started with Cramer in 1938, who was looking for applications in insurance. And I also mentioned it. So there's a kind of back and forth in the theory between physics and mathematics, and this is the point of the title, from physics to maths and back, because now actually a lot of results have been found on the mathematical side, and they're being applied in physics with new applications, and I'll try to give you an idea of these applications near the end. Okay, so I'll start with how the theory started in physics with the next slide, which is this calculation, as I said, by Boltzmann. So this is something that physicists know, but I'll just present it very in depth. So the idea of Boltzmann is that you want to study a system like a gas. So you have many particles, and they're like, you have the dots here at the different levels. Is it showing here now?
No, it's showing.
No, it's showing, okay. So you have the different particles. You have particle 1, particle 2, particle 3, and so on. You have n of them, and then they have different energy levels. So particle 1 can be on the first energy level, particle 2 and 3 can be on the second energy level, and this is the microscopic configuration of the system. You can enumerate what each particle is in which state, and this will be the microscopic configuration. But as a macroscopic observer, this is not what you see. So what you see instead will be something like a distribution of particles, the actual histogram of the number of particles in each of the state, and this is what we call the energy distribution. This will be the number of particles in a certain level J here. And the idea is that you have many actually microscopic configurations that will lead to the same energy distribution, the same histogram. And the point is to determine, okay, which one is the most probable? Which one are you going to see? So then you have to do a kind of combinatorial problem where you have to count the number of microscopic configurations leading to a given energy distribution. This is the calculation that Boltzmann did. And if you have many levels like this, then this is actually the multinomial distribution. The probability to see a given histogram of the particles in certain energy level J will be given by the multinomial distribution. So here I'm only showing the multinomial factor, and if you expand it with Stirling, then you get the entropy of that histogram with that distribution. The point is that now if you look at the distribution, at the probability to see a given histogram of the particle distribution, then this will go exponentially with the number of particles, and the exponent will be the entropy. And so you see there's a probability that behaves exponentially, and this will be the theme actually of the theory, and actually the basis of the theory that will show up over and over again in applications. So this is a calculation that was done in 1877. This is I show here the paper where you see M is the entropy, it's the P log P. So for Boltzmann you have the W for the distribution, the log is the L, and here you have the number of particles and the energy constraint. So you want to maximize that entropy with these constraints. And I'll get to this later on. The main point again is that you have a distribution that behaves exponentially with the number of particles here. So that's the number of components. Okay, so this is the basic calculation. And then later on, so this is a calculation you can do only for what we call the perfect gas, so particles that have no interactions, because you're just counting them in different energy states. There's no energy actually describing the interaction. So then later on in 1910, Einstein actually tried to generalize that calculation to say, okay, how can I do the same kind of calculate the distribution, the probability for a certain distribution, but for a gas, say, that's interacting. So it's very complicated. It's probably impossible to do the counting or the combinatorics. So what he did instead is to invert the idea. He would say that, well, I know how to calculate the entropy for a general system, so I'm just going to postulate that the distribution is given by the entropy, whatever that entropy is for a specific system. So this is what we say, it's the kind of inversion of Boltzmann calculation, it's Einstein's postulate. And so that postulate essentially says that any kind of probabilities that will happen in physics if you're dealing with many systems will behave exponentially with that number of particles. So you have the probability behaving exponentially with the number of particles, and then you have the entropy. And so what we call the equilibrium state, which will be the most probable state that you'll see in a system, will be the one that maximizes the entropy. So this is a kind of phenomenological way of writing probabilities in physics, but we'll see that it has a basis later on in the theory. And I'm showing here actually the paper, the bit of the paper of Einstein where you see that you have the probability that behaves exponentially, and then you have other constants. R is the actually Boltzmann constant in the physical context. Okay, so you have two hints that probability in physics behave exponentially whenever you have many particles interacting. Then we'll come back to this. Okay, so these are the first two calculations from physics, and then it doesn't really give rise to any mathematical theory as such. It's just actually part of what we call statistical physics, how you describe distributions for many body system or systems with interactions with many particles. So now I come to the birth of the theory on the mathematical side, and the context is very different, but the point of the talk will be to kind of merge that mathematical theory and then come back to physics to see that they're really the same. So the starting point for Cramer was to look at sums of random variables, which at the time were studied a lot. So this is back from 1938. So here you have a sum of random variables. So this is a very mathematical problem. And for simplicity, he looked at the case where you have independent random variables with the same distribution. So independent and identically distributed random variables, i.e. random variables. And the reason for Cramer to look at this was that he was really interested in insurance problems. So you have basically a sum of random claims, and you want to get the distribution of the claims to fix then the kind of price that the insurance should be charging to cover these claims. So the idea also was to go beyond the Gaussian approximation. You can try to find a Gaussian approximation of the sum, but it's not good enough for insurance companies because you really want to have good information about the tail of the distribution, because this is where the large claims will come, and then you want to cover yourself from these large claims. So you want to have detailed information about the distributions. It was looking for something that goes beyond central limit theorem as such. So the result he found was that the distribution of the sample mean, so this is the sum divided by n, so this is called the sample mean, also goes exponentially with the number of random variables with an exponent that's to be calculated. And then he was able to get all the corrections, and the main point to see is that all the corrections are very small compared to the exponential. So really the dominant part of the distribution is that exponential. It's decay exponentially with like the square root factor here for corrections and so on. But if you forget these factors, then you really have an exponential distribution. Moreover, it was able to get an explicit expression for what we call the rate function. So this exponent in the exponential, this is the Legendre transform of the cumulant. So this is really now a solved problem. You have just get a sample mean, you choose the distribution for the random variable, you can calculate the cumulant, and then you can calculate the Legendre transform, and then you get the exponent that characterizes the dominant part of that distribution. This is very useful. And then here I'm showing the historical paper actually that was written in French in 1938, which has been translated now. So this is now for ID random variable, and it's very interesting that you have the kind of very similar distribution as we see in physics. And then again, I'll come back to that relationship. So this is the start of the theory. Not much was actually done from 1938 until 1957, when you have a Russian mathematician, Sanov, who looked at a slightly different problem, but it's actually related. So here the problem is to look at the distribution of a sequence of random variables. So this is very much like Boltzmann problem. So to fix the idea, imagine that you're just putting random coins on the table. Suppose you have like 50 coins, and then you just flip them, and then you're looking at the ones with heads and the one with tails. And then you can look at the empirical distribution. So I have a sequence of heads and tails, n of them, with certain distribution. So for heads and tails, it will be 1/2 for tails and 1/2 for heads. It could also be like zeros and ones, so you have a binary sequence if you want. So it will be the same thing. And then I can look for a certain sequence at the empirical distribution. So I can count the number of heads divided by n. This will be the fraction of heads. And I can look for the tails, the fraction of tails, just by looking at. So here I have a sum, really, of ID random variables, but I'm just summing ones or zeros depending on whether I see that a head or a tail. So this is a random variable. In fact, it's a random histogram. It's a random vector, if you want. If I throw another sequence of heads and tails, then I'm going to have a different fraction. And then if you start actually doing this experiment yourself, you realize that it's very unlikely that you get all tails or all heads. So the most probable fraction will be 1/2, 1/2. But what is the distribution exactly? Well, it will be the binomial distribution. You can approximate this also with Stirling approximation, and then you find that the probability to see a certain fraction, to see a certain vector of fraction, will go exponentially with the number of heads and tails you have on the table. And then the exponent that shows the decay, so the rate function, is what we call the relative entropy. This is exactly the same result as Boltzmann, but it's just in a mathematical context. So Boltzmann was looking at the case where the random variables were the energy levels of the particles in the gas, but this is more the abstract problem where you have just a sequence of random variables. And out of this, now you can really calculate the distribution. You can ask questions like, what's the most likely fraction? Well, it will be the fraction, it will be 1/2, 1/2, and then you can calculate this from the relative entropy, because the zero of the relative entropy is when rho is equal to t, the distribution that you use to sample the random variables in your sequence. So this is the next result, 57. This is actually 80 years after Boltzmann. And what's interesting in that paper is that there's actually no mention of Boltzmann whatsoever. There's no connection in physics, and the problem is presented really independently as a mathematical problem with no sources coming from physics. So this is quite interesting. If you're a physicist and you're reading this, you see really how the two theories developed completely independently, and it's only later on that connections were made. Another interesting thing about this result is that this is the only result of probability theory coming from Sanov. Sanov actually is not really known as a mathematician in probability, although this result is widely known in large deviation theory and also in information theory. Surprisingly, the claim to fame of Sanov was that he was sent in the 50s to North Korea to oversee the development of mathematics there, and then came back, and then after that worked for the KGB. But that's about it. I don't know much about Sanov. It's very difficult to get information. This is a picture I found of Sanov. I think it's Sanov. I'm not entirely sure, but if you have any information on your side, or I'll be interested to hear about it. Okay, so this is the second result in large deviation theory. Again, not much really happened from there, but the theory really grew after that in the 60s, and I'll present some results about this. But now I'll just sort of present the theory as we know it now. So you see, you have distribution like Sanov results or Cramer's results that show that the distribution is decays exponentially with the number of random variables. And so you start feeling that this is something that will happen a lot in many contexts. And indeed it does, and not just for ID random variables, and I'll present this. So you can start building a whole theory about these distributions that decays exponentially, and this is the point of large deviation theory. So the starting point is that you have a random variable. It could be like a sample mean. It could be also a histogram, a random histogram, like in Sanov's case. So it's quite general. It's a family of random variables. It's indexed or parameterized by some n, and n will be going to infinity at some point. But n can be many things. It could be the number of random variables you have in a sum. It could be a random product. It could be something else. I'll show other examples where the nature of n is very different. And the point again is that you want to calculate the probability distribution or the density of that random variable, and in general this is very difficult. Even for IID sum, finding the distribution is not so trivial. But what you see again is that there's a very general approximation, which is this large deviation approximation, the fact that it decays exponentially with the number of random variables. And that observation is actually a definition in large deviation theory. It's what we call the large deviation principle. So the meaning of the approximation, again, is that anything will be sub-exponential if you look at the exact expression of the distribution. And so the dominant part is really the exponential. So that if I take the log, I'm going to see the linear part, which is the exponent, plus corrections that will be smaller than linear, so small O with n. And if I take the limit, then I can kill the correction here, and all that will remain is the rate function. So we say that we have a large deviation principle, or that the random variable satisfies, or that the distribution satisfies the large deviation principle if the limit here exists and gives you a function that's not everywhere 0 or infinite. And this is the rate function. So you see really if I have this limit, then it really means that I have something that controls the exponential decay, and that really is the dominant part of the distribution. So in mathematics it's slightly more involved. Actually here I'm only presenting a simplified version of the large deviation principle. Mathematically you'd have an upper bound and a lower bound are also exponential, and in many cases the two bounds are exponentially the same, so you can sandwich them and then have that limit. So this is the basic, really, brick of the theory. And so the goals of large deviation theory in that context is to, if you have a specific random variable, you want to prove that you have a large deviation principle underlying the distribution, and you want to calculate the rate function. Once you know the rate function, you know more or less everything about the distribution, and I'll give examples of that. So you know the distribution really at the exponential order, at the dominant order. And any corrections, again, will be kind of irrelevant compared to this. If you know the power of the exponential, any polynomial corrections, for instance, will be very small compared to the exponential. Okay, so that's the theory. Now, how do you get rate function? So there are many techniques in large deviation theory to get the rate function, the main function that you want to study. I'll present only one, which is the main result that we use actually in physics and applications, also say in queuing theory to get large deviation probabilities, which is called the Gärtner-Ellis Theorem. So the idea for this theorem is that instead of trying to calculate the distribution directly, you look at moments or at generating functions. So if you get some information about the generating function, then you can kind of use that information to get the rate function. And this is the point. So the starting point is you have that random variable here that you're interested to study, and then you calculate the generating function. So this is the expectation of the exponential, and then you have n and k here. K is just a parameter, a real parameter for the generating function. Now, if the distribution behaves exponentially, there's a kind of hint that you should look now at the generating function also on the exponential scale. And so you put the log here in a certain limit, and the point is that you want to calculate this function. And if this function exists for all k real, then you can actually get the rate function, and this is the theorem there. So the theorem dates back from Gärtner 77, and it was later on generalized by Ellis in 1904. So the basic statement here, I'm presenting really just a simplified version, is that if you can calculate lambda k, it exists, and it's differentiable for all k, then you have really the two things that you're after. The random variable satisfies an LDP, so a large deviation principle, and its rate function will be the Legendre transform of this, what we call the scale cumulative generating function. And in this case, you know also that the rate function will be convex. So this is really useful, and I'll show some examples of application. It really simplifies the calculation of distribution amazingly. But it's all based, of course, on trying to calculate this and being able to calculate this function, which is not always easy, but it's very easy for certain cases. Sure. Okay, I should say that there are other results to get also to the LDP and the rate function, but again, this is the main one. So it's not just that the whole theory is based on that result, but it really is the main. So Let me give you two examples. So let's go back to this simple mean that Cramer looked at before. So again, we have a sum of random variables. We divide this by n, so we call this the simple mean. So if I take many such variables, this will go according to the law of large number to the mean of the random variable, but there will be fluctuations around the mean, and this is what I want to study with the distribution. So I take again xi to be distributed with some distribution p of xi. So I can look at various cases. You can plug your favorite distribution in there. So for instance, if we take the Gaussian case, so I'm just looking at a sum of Gaussian random variables, I can calculate the lambda k. It's fairly easy. In fact, I'm showing here, for I, the random variable, the limit really simplifies because the sum here and the exponential will factorize. You can factorize the expectation because you're dealing with independent random variables. And because they're all the same, they're all identically distributed, then you end up with just a cumulative, just like Cramer. So really, this result now for I, the random variables, the Gärtner-Ellis Theorem, reduces to Cramer's theorem for I. So again, I can go to the Gaussian case. I can plug my favorite distribution, calculate the cumulant. The cumulant is known in this case as a parabola. It's differentiable. It exists for all k real. So I can take the Legendre transform, and I get also the parabola, which is here. So the rate function is always positive. In many cases, it has 1, 0, which in this case is the mean, because we know that as n goes to infinity, the distribution will concentrate on the mean. And then what the large deviation principle tells us is that the tails decay exponentially with the number of random variables. So you see that n equals 10, n equals 100, n equals 500, and so you have this concentration. And what I can say is that I have exponential concentration because everywhere the rate function is positive, the tails will decay exponentially. And the higher the rate function, then the greater, the faster the decay to 0. And here, the rate function is a parabola, and this is consistent with what we know anyway with sums of Gaussian random variables, because the sum of Gaussian is Gaussian. So the exponent really will be a parabola. What's interesting is that now if you take out the distribution, then you don't get parabolas. So really, you're going beyond the central limit theorem. For instance, I can take exponential random variables. I can calculate the cumulant again. This is the answer here. It's also differentiable, not for all k real, but where it's defined. And I can take the Legendre transform, and I get this function. So now the rate function is the red line. You see that it's defined only for positive values of the random variables because I'm dealing with exponential random variables, but I have the same concentration, exponential concentration, which is defined by this rate function. I have a 0 of the rate function where the distribution will concentrate, but now you see it's not a parabola. So for instance, here, close to 0, I have a decay that's much faster than in the tails. And in the tails, I can say, well, because it looks like linear, then I have a kind of exponential decay, but purely exponential in decay. So the rate function, you see, gives me lots of information about how I can calculate distribution. And that's the point again. It gives you like a picture of the distribution, how events are likely or unlikely. So here I can say the mean is very likely. It's the typical value, whereas away from the mean, I have unlikely values that will decay according to this rate. Moreover, you can do actually a Taylor expansion around the 0, and this will give you Gaussian information about the fluctuation there. Because essentially you have a parabola, which means you have Gaussian fluctuation. But that's only close to the mean, so that's the central limit theorem. Away from the mean, it's highly non-Gaussian. Okay, so this is for independent random variables. You can play that calculation for other distribution, but you see again, it's much easier than attacking the distribution directly. Really, the whole calculation boils down to calculating a cumulant, which is much easier. It's only for one random variable and then calculating the Legendre. Okay, so you can, here's another example, but I think I'm going to skip this one. It's very much like the sum of the Gaussian. Here you can sum actually Gaussian squared, and then you can relate this to geometry, but this is very similar to the previous example. I'll just go back now before moving to applications in physics, try to come back to the Sanov's theorem. So again, the idea of Sanov was to look at a histogram as a random variable. So you have a vector of random variables, which were the empirical frequencies. So again, just to fix the idea, imagine that you have zeros and ones. You're just throwing at random zeros and ones, so a binary sequence of heads and tails at random on a table, and then you look at the fractions of zeros and the fraction of ones. So you have your empirical vectors of fractions of zeros and ones. So we saw that the distribution of that random vector goes exponentially, but that came from a direct calculation of the distribution. So here I can try to apply Gärtner-Ellis, and I can. So I can calculate now this lambda k. The only difference is that I have to deal with a random vector rather than just a random variable that is a scalar. So k has to be a vector too. This is the scalar product. I can calculate this exactly, and this is now this is the cumulant function for the distribution for that random vector. This is differentiable in the vector sense, so I can calculate a Legendre transform in the vector sense, and what I get is the relative entropy. So really, it matches the calculation that was done explicitly using Stirling approximation, but now I'm only using a transformation, the cumulant and the transformation of the cumulant to get the right function. So this is much more powerful now by going via this Gärtner-Ellis theorem. Okay. So, this is it's quite fun to apply if you look at ID random variables. It's a powerful theory for sums of ID random variables, but it would be so much of a theory if it was only applicable to ID random variables. So the good thing about the theory is that you can apply it much beyond this kind of example, especially to Markov processes. And this is really the pinnacle of the theory and how really it developed as a theory. It's work from Donsker and Varadon in the 70s that really pushed the theory to first define the large deviation principle in a rigorous way, and then show that also sums of random variables related to Markov chains or integrals of random variables related to Markov processes also had a large deviation principle. So this is a bit of a template of the application and something that's used a lot in physics. You imagine that you have a Markov process evolving in time. Now you look at an integral of some function of the process. So this is a bit like the random sum, the sample mean I had before, but now I replace the number of random variables by the total duration for the integral. So capital T is the time integral up to capital T. And now the large deviation principle will decay with that integration time. So the longer the integration time, then the more concentration you have for the distribution. And this is characterized by the large deviation principle. So in this case, we're dealing with a long time limit, not just a large number of random variables. This is the basis of many applications in queuing theory, but also in physics. And at the same time, actually, that Donsker and Varadon were working in the 70s on this theory, there's another theory that was worked out by two Russian mathematicians, Freidin and Wenzel, who looked at a very different context. So the context here is that you look at dynamical system described by a differential equation, and then you had some noise to it. So you have now a stochastic differential equation. The simplest case is that you look at Gaussian white noise as the driving noise for the equation. And what you can show is that when the noise becomes really small, when the amplitude of the noise becomes small, you have a distribution for the trajectories that will concentrate also exponentially, but with the inverse of the noise amplitude. So this makes sense because when the noise actually becomes smaller and smaller, most of the trajectories will concentrate along the deterministic trajectory of the differential equation. So you have this concentration now with the noise amplitude. And this is really a large deviation principle. It's just a very different one. It's a large deviation principle on the space of the trajectories. But it has the same form. And this is something that was applied, actually developed also independently in physics by Zager and Macklup in the 50s, so even before it was developed in mathematics. And these two large deviation principles are the basis of all the other applications. So I'm not going to mention all these applications, but I'm showing the list here. You can apply this to random walks or Markov chains, essentially noisy dynamical systems like this one here. Also PDEs, so partial differential equations. If you look at stochastic partial differential equations, you also have large deviation principles in there. Random graphs, you can look also at very large graphs like Erdős-Rényi graphs, and then look at typical properties of these graphs, where you can look at random walks on random graphs and then find large deviation principles. Queuing theory, I've mentioned, statistics and estimation theory, you also have concentrations that follow large deviation principles, and information theory, the last. There are actually more applications. The point is that whenever you're dealing with a system with many components, like many particles, a long time span, or in this case you don't have many components, but you have a small noise, then you have distributions that will concentrate exponentially, and that exponential concentration is described by a large deviation. And so the next step is, I'll try to show how we apply this to physics, but this is the summary of the main observations so far. So the point, again, is that you have a distribution for a general random variable, so we don't specify the nature at this point of what that random variable is, but the point is that the distribution in many cases will have this exponentially decaying form that we call the large deviation principle, and so all the information and what we want to study really is that rate function, I of a. So that, in general, you have a rate function like this, but it doesn't need to be like this. The rate function can be very complicated, but it will give you still information about the tails of the distribution and how the tails decay with A. So for instance, if you have something like this, you see you have a 0, so this is where the concentration will happen, but you have here a local minima, so here you have a decay of the distribution, but not as fast as this part here, and so we call this a metastable state. But that rate function will give you a picture really of how the distribution behaves as n goes to infinity. And so there's a few things I've mentioned already. I've said that the typical value, so the 0 of the rate function is where the distribution will concentrate. This is a large number in the context of sums of random variable. As n goes to infinity, the sum concentrates to the mean, and so this is where the 0 will be. I also mentioned that even if the rate function is not quadratic as such, you can expand as a Taylor expansion here in a quadratic way, and then so you'll get local fluctuations which will be Gaussian, and that's the central limit here. But in general, the rate function again is not quadratic, and so we say, so it describes small and large deviations that will be non-Gaussian. So it's from that point of view, it's a general theory of fluctuations, but also a typical state because it describes where the concentration would happen. And so this is the general picture. This is the general picture that arises a lot in physics, especially, but also in other fields. So what I'll do now is to switch to physics, and I'll try to give just a taste of how physicists apply this theory to describe many particle systems, but also systems like weather systems or temperature maps and so on. The simplest, I guess, and the oldest and the first application, if we're looking back at Boltzmann, is a system of particles with a fixed energy or a fixed temperature. So we call those systems equilibrium systems, so they're not forced in any way. They're just in contact, say, with a bath at fixed temperature, or they have fixed energy. So the way that we describe a system like this, we use probability, but is that we define a distribution over the microscopic configuration of the system. So you have a system with n particles. So imagine that you have a kind of a vessel of gas, and then you have all the particles, and then the system is at a constant energy. So we have n particles, and then from a physical point of view, I can enumerate each particle, what is the state of the particle. That's what we call the microstate, the microscopic state. So particle 1 will be in the state omega 1, particle 2 will be in the state omega 2. So this is how you would describe the system in a microscopic way, but this is not, of course, how we see the system in a macroscopic way. And so this is why we need probabilities now to describe that system. So we assign a certain distribution over the different microstates. And what we do is that we actually measure something else. We measure what we call a macrostate. So it could be the magnetization of a spin system. It could be the mean speed of a gas system. It could be the temperature of that system. So this is something that will involve actually all the particles together, which is why we call it the macrostate, macroscopic state. And the point of statistical mechanics, the point of what physicists do at that level is that they want to calculate the distribution of the macrostate given the probability model for the microscopic states. So this is just, for the probability to get a certain value for the macrostate is just the sum of all the probabilities of the microscopic configurations that have that value for the macrostate. Okay, so it's really general as an approach, but that's really what you want to do. So what you want to do is to calculate that distribution. But again, this is something that is very difficult to do in general because it involves many particles. But this is what the task is. And out of that distribution, you would find the most probable value of the macrostate, and this is what we call the equilibrium state. So for instance, if you look around you, if you look at the table, you don't see any fluctuations, even though the table is made of particles at the microscopic level. If we were able to look at those particles, we would see fluctuations, we would see tiny movements of these particles. But what we see at the macroscopic level is very stable, is very uniform, because what we see is the equilibrium state. It's the equilibrium state of some kind of composite state that is actually made out of the particles. So this is the most important task, actually, is to find the most probable value of the equilibrium state out of that distribution. But in many cases, we're also interested in looking at the fluctuations around the most probable value, around the equilibrium value. This is done by taking what we call the thermodynamic, where the number of particles goes to infinity, because we're dealing with very large systems. And so we have that limit just to represent very large systems. So for instance, if you look again at the table, you have something like 10 to the 23 plus particles making up the table. So you have this huge concentration. So you have tiny fluctuations, which, as we'll see, they're exponentially small. So this is why we see that stability for all the objects that surround us. So this is the starting point. This is the problem as such. Now, how do we attack that distribution? Well, this is where we start to use large deviation theory. So the calculation actually goes back quite a lot, even before large deviation theory, because it's part of statistical mechanics. So you have the names here, Einstein 1910 and Landau 1937, because these were calculations that were done actually before. The point again is that the distribution of the microstate will go exponentially with the number of particles. But that is not made explicit as I show you. So first I should say, there are many different situations that you can imagine looking at physical systems. You can have a system with a fixed energy, or you can have a system with a fixed temperature. So this should be two different probabilistic models. And indeed, in physics, we just call them differently. So this is what we call the microcanonical ensemble. So it's a probability model that describes any system with a fixed energy. And then we have something else called the canonical ensemble, which is a probability model that describes any system that has a fixed temperature. In both cases, though, what you'll see is that the distribution of the microstate will be exponential. So here, the distribution will be parameterized by the energy, because if I change the energy, I'm going to change the distribution. But you see, the LDP will tell you that the distribution approximately goes exponentially with the number of particles, with a certain rate function that tells you how quick or how probable the different values of the microstates are. So from that point of view, I can also look at the equilibrium state. The equilibrium state will be the most probable state, so it's the one that minimizes the rate function, and then we know it's the one that actually achieves the zero of the rate function. Equilibrium state from the mathematical point of view is just the minimum and the zero of the rate function. Now the same thing will happen if I look now at a system with a fixed temperature. So I have my little system here. It's in contact with something with a fixed temperature, so my system is also at a fixed temperature. And then the distribution, as we can calculate actually from techniques in statistical physics, will end up being exponential with the number of particles, with a certain exponent that depends on the temperature. So here I put the inverse temperature, and then a rate function that is specific to our system. So if you change your system, if you change your microstate, then you'll get different rate functions. But the point again is that that distribution is described on the exponential scale with the number of particles in the rate function. So this has been done for many systems. This is actually the basis of what we call equilibrium statistical mechanics, which is to find what are the equilibrium states of specific systems like liquids or solids, and then we also study phase transitions out of this. And just as an application, I'll show you here how we apply this to a perfect gas. So here, in a way, I'm going back to Boltzmann. In the way that I look at a system with many particles. So I just have a schematic here. So this is supposed to represent also a volume of gas with different particles here moving. So I'm not showing the movement, so there's no movie. But imagine that the particles are just moving chaotically. They collide with each other. And I'm just coloring the particles according to the velocity. So the red ones will be high velocity, and the blue ones will be low velocity. So you see, even if I have a fixed energy for the whole system, the energy will be distributed differently according to the collisions between the particles. And so I'm going to have particles that move fast and particles that move slow. This is what, if I have a big enough microscope, I could look at these particles and then see that movement and then see the different velocities. But of course, we don't see this again. On the microscopic level, if I look at a gas, I don't see the particles, but I feel something very uniform. I feel a constant temperature. How is that? That's because there's a mean velocity, and then there's a concentration of the distribution of the mean velocity onto the mean velocity. But there's a deeper way to see this. So I can do like Boltzmann. I can count the number of particles with a certain velocity and divide this by the number of particles. And here, just to normalize the density with some velocity increment. So, for instance, I can just freeze I can freeze the movie, or I can just like take a picture of my gas system and then go into counting which particles have high velocity. But I have very few of them. Which particles have low velocity? I have few of them. So most of them will be a bit like this. Now I can run the system again, I can let it evolve, and then take another picture and then calculate this histogram again. It's clear that the histogram will change. This is a random variable. This is a random function in a way. Okay, so depending on how the energy is distributed, then I'm going to have different distributions like this. So I can play the same game as Boltzmann. So here I'm just counting the different particles and the different energy levels. Here the energy levels will be the different velocity. And then I can ask now, what is the probability to see a certain histogram of velocity? Well, this is the same question that Boltzmann was asking. This is also the same problem that Sanov was studying, because we're dealing at fluctuations of a random vector. It's actually here fluctuations of a random function. And then we know from Sanov, and then we know from Boltzmann, that the distribution goes exponentially with the number of particles with a certain rate function, which I can calculate. So here I'm not going to calculate this, but what I'm going to show you now here, what I'm showing is the zero of that rate function. The most probable velocity distribution, it's the Boltzmann distribution. It's actually what we call, sorry, that's the Boltzmann distribution, the Maxwell distribution for the velocity. And this is now the black line I'm showing you. So it could be that by taking a picture of the system, I have many particles with high energy, but this is very unlikely. It's also very unlikely that I have many particles with very low velocity. The most likely distribution of the velocity is the Maxwell distribution. And how likely is it? Well, it's exponentially likely. So the more particles that you have in your gas, then the more likely you see that distribution. And you can imagine if you have 10 to the 23 particles, that n is really large. So the exponential is really dense. So you have really a distribution that's highly, highly peaked around that Maxwell distribution. So all I will feel, all I can measure is something that's very regular, and it's that Maxwell distribution. So this is the explanation of what we call thermodynamic stability. The fact that even though everything is made out of particles fluctuating at the microscopic level, what we see at the macroscopic level is something that has no noticeable fluctuation. And the reason why we don't see fluctuations at that level is because they're exponentially unlikely, and n is very large at that. Again, if you look at much smaller systems, then you can start looking at this fluctuation, and this is what physicists do a lot these days, is to look at smaller systems and try to measure fluctuations and infer physical properties from the fluctuations. Okay, so here I just wanted to give you an idea of how we apply this. So there's been many more applications in physics of the formalism of large deviation theory to study typical states and fluctuations, and here I'm putting a list. We have spin systems, Bose-Einstein condensation, phase transition in general, but also it's been applied to look at turbulence. So often in turbulence, then you can model turbulent flows using stochastic processes, and you can look at the most probable configurations of the turbulent flow or stable properties of the turbulent flows that will arise out of concentrations of the large deviation property. And a lot of applications now that are being studied are related to quantum systems, quantum information, quantum computing. There's also some work on machine learning related to spin glasses. But the main point I want to put here is that in all these applications, and very generally in physics, whenever you look at many components, you have a large deviation structure. Namely, any type of distribution that you're looking at will have this exponentially decaying form. And so the goal is to look at rate functions and calculate these rate functions to characterize the typical state of your system, but also the fluctuations of your system. And as an aside, also when you apply the theory, you realize that what physicists call the entropy is really just a rate function. So mathematically, you can interpret or you can give meaning to entropy as being a mathematical function that is the rate function. Okay, so this is the bit of the application. I just want to show you maybe just a panorama of other applications, and this is the more or less the last slide. So there are many more applications, and a lot of the current work actually that we're doing, that is being done in physics, is not so much on equilibrium systems, but what we call non-equilibrium systems. Now, what are non-equilibrium systems? They're a system in which you have an active force into it. So you imagine if you just have a gas in the room, or you have like a balloon, it's not forced in any way. It's at equilibrium, it has a constant temperature. But maybe you can have a system where you have two temperature heat baths. So you have, say, like a slab of metal, and then you put it in contact with the high temperature system on this side, something like a hot body, and then a cold body on the other side. And because you have two different temperatures, there'll be a heat current between the two. And so this is a non-equilibrium system. You're driving the system away from equilibrium. You have a current. There's a kind of thermodynamic force that's just pushing energy from one side to another until the two heat baths would actually equilibrate. You can have the same if you have many particles, so different density or different chemical potential. If you have many particles here, and then you have a kind of repulsion between the particles, they will tend just to go away, spread out. And they can spread out via a channel to a place where you have fewer particles. So if you have high density and low density, then you will create also a current, and will be a current of particles. So this is a non-equilibrium system. It doesn't have like a fixed temperature because you have two temperatures here, or you have two chemical potentials here, and so it's driven out of equilibrium. But you can imagine that you can play the same type of game. You have a microscopic system, you can put a microscopic model onto it, so a kind of distribution for the configurations, and then you can look at the distribution of a macro state to see what is the most probable state of the system, what is the most probable, say, current of particle or current of energy here, and then you'll have a typical current, a typical particle current here also, with fluctuations that are very small depending on the size of your system. And so this is what people study a lot under the term of interacting particle systems. So you have many probabilistic models of these systems where you can actually, based on Markov processes, where you can calculate the distribution of the different configurations or the different trajectories of your system, and then from there calculation large deviation. So this is one big area of research at the moment. Another one is what I mentioned, turbulence. And here I'm showing something related to weather patterns. I'll start with turbulence, and sometimes in turbulent flows you have bistability, where you see a turbulent flow is actually has some kind of vorticity field, and then suddenly it switches to another vorticity field kind of without any forcing. Sometimes you have forcing, sometimes you don't need forcing. And then, but it's a rare event in the sense that you have very long period where the vorticity stays the same, and then it switches. And then what's known is that, what's been found actually, is that the switching is also a large deviation principle. So it's exponentially unlikely that you have switching, but you do have switching on very long time scale, and then you can characterize the switching by an LDP, which is essentially a bit like the low noise LDP I mentioned before from Benson. And this one now, related to temperature anomaly, is something quite interesting, something that was done actually last year, so it's very recent. It's to look at weather patterns that are very atypical. So for instance, if you look at summer periods in Europe and winter periods in Europe, then you know you have a kind of average temperature. So average summer temperature, average winter temperature, and the weather, even though it's different every day, if you average over different seasons, it's very much stable. So temperatures don't really depart significantly from averages. But sometimes you do have large fluctuations, and this is a fluctuation that was studied. It's a particular fluctuation. It's a very hot summer actually in 2000, I think it was 2006 in Northern Europe, where you had really high temperature for about 2 or 3 weeks in Northern Europe, so around Russia and in Scandinavia. And this is seen as a large fluctuations, as a rare event. And the point of the study was to calculate, okay, how rare is that event? So you can start by modeling the weather system using stochastic processes. So you have here some sort of weather model involving many different parameters, actually, like humidity, temperature, and weather patterns moving around the northern hemisphere. And then you can simulate this, and you see events where you have large anomaly of temperature in the summer, and then you can calculate the probability. And what you see is that it also, the distributions of these anomalies decays exponentially with a certain parameter, which is essentially the observation time. So this is quite interesting, and this is also general in other systems where you have distributions that decays exponentially. It just shows the power of it, but here the difficulty is really to come up with a model that enables you to calculate the small probability for the anomaly. But you see the picture. So I think This is the last slide. The last slide is just a conclusion, a kind of dictionary between physics and maths, how you apply large deviation theory in physics. And so this is something we've seen, but I'm just summarizing what I was discussing before. So on the mathematical side, you'll be playing with random variables, and in physics, you call those actually ensembles, but it's basically the same. And then if you go to Markov processes, then you'll be dealing with stochastic processes. And what you want to calculate are distributions of macro states, which could be sums of random variables, and then you look at typical state, typical values, which in physics are called equilibrium states, and in maths, most probable values. And then the theory is also about the fluctuations around these typical states. So fluctuations are then you have the connection between mathematics and physics. What mathematicians call a rate function is what physicists will call an entropy. A Coumadin function is also something that we call the free energy. I haven't mentioned this, but it's also another interpretation of something, physical quantity that shows up in statistical mechanics. And then what's important in all of this is that you need to have a scaling limit. So a system that has either a large number of particles, or you're observing your system for a very long time, or you have the noise amplitude going to zero in some way. And then you're taking that scaling limit because you see that the distribution has that scaling as you take the limit. And what's interesting, and then it's probably what I mentioned last, is that this is useful across many different applications because you have one language to describe many different things. And then in physics, it's been very useful to actually put the theory on a rigorous basis, but also to spread a kind of unified language to talk with mathematicians and have a unified language also across physics for people to realize that they often deal with the same problem in the same structure mathematically. So it's been something very useful for us, and I think useful for mathematics as well, because many results coming from physics have made their way through mathematics, and I've pushed actually the theory in a wider sense. So I'll finish on this. If you want more details, I'll invite you to look at this review paper. So this is a review paper that I wrote actually about 10 years ago, but you'll find applications mostly in statistical physics, but there are also lists of applications in mathematics. And then you can find more details about applications outside of physics on my website and the kind of research I do if you're interested. So I'll thank you for your attention.